Hello, everyone. My name is Danny Xiao. Thank you for coming to the last engineering seminar series of this semester. So first, a quick introduction of the engineering seminar series. It's hosted by UW-Platteville starting 2016. The seminars are 1 hour-long presentation of real-world projects that showcase the plan, design, construction, maintenance of engineering projects and how they can change our community. Attendees are eligible to earn 1 professional development hour. To minimize the background noise, all attendees on Zoom are muted during the presentation, but you are welcome to type in your questions during presentation. And then at the end, we will have a Q&A session. You are free to unmute yourself and ask questions, or you can type, and then we will try to get to your questions as many as possible. So yeah, today we have our very own, my colleague, Dr. Augusto Gill, talking about exciting high temperature and its impact on structures. So I'll do a quick introduction and then we'll give the floor to Dr. Gill. So Dr. Augusto Gill is an assistant professor in the Department of Civil and Environmental Engineering at UW-Platteville. He teaches courses in the structural engineering emphasis. His research focuses on advancing the fire safety of structural systems, including concrete, steel, and timber buildings and bridges. His work combines experimental testing and numerical modeling to evaluate the degradation of material properties at elevated temperatures and its effects on structural performance. So we're very happy to have Dr. Gill share his research and the significant impacts to the structural integrity of fire. So again, help yourself for the food, drink, pizza and drink. We want to acknowledge the food is provided by the colleagues. So thank you for the sponsorship or to offer us food. So without further ado, please help me welcome our speaker, Dr. Gill.
All right, so good evening, everyone. Yeah, we are going to talk about a hot topic, right? It's cold and rainy outside, but it's going to be hopefully warm in here. Thank you, Danny, for organizing the seminar series and for inviting me to give this talk. I'm very excited to share a little bit about what I do outside of the classroom with the students and with my colleagues over Zoom. When we think about structural design, right? A lot of people who already work in structural engineering, they know we need to do some checks for fire safety. Okay, we got to make sure that our structure is not going to collapse if there's a fire, right? So if we are all here inside of this building, there's a fire, we got to make sure this structure remains standing in order for firefighters to come in, put out the fire, and for us to have enough time to go out, right, safely. And most of the fire safety regulations or the way we do this type of design is based on what we learned from previous experiences. Okay, so when you guys think on very big fire incidents or events that happened, do you guys remember any big fires that happened before? Anyone? Sorry? The tribal choice factor. Okay, yeah, that's a good one. So there was a factory, right? An industrial fire. Danny? The Great Chicago Fire, right? So kind of a city scale big fire. Anything else? Something more recent, maybe? LA, right? We had a very big bridge fire early last year in LA. So very good. So whenever there's like such big events like this, especially those of very high magnitude, there's a big change in regulations. Okay, so the Chicago fire was a big one because, for example, the biggest change that happened in construction industry after that one was we learned that we need to have spacing between our constructions because fire can propagate from one building to another. When we have, for example, bridge fires like in LA, a lot of people don't know that, but our bridge structures, they're not designed for fire. So if there's a fire in a bridge, there's going to be significant damage or even collapse. So after, for example, the LA fire, we're going to talk about another similar case here later today. There's some sort of discussion. Should we include that in our design codes or not? Okay. I'm going to bring up here just two examples of kind of similar scale fires that changed a lot the way we design buildings and structures. The first one over there was the Greenfell Tower in London, 2017. So it's not that long ago, right? So 8 years ago. Do you guys remember what happened there? Have you heard about this fire? No. So actually, Netflix just released a documentary talking about this. So if you guys are interested in learning more, it was very interesting. But basically, they have this cladding material.
Adjust the camera very quick. So you're talking about the camera is not right. Hold on. Sorry to interrupt. I'm gonna move this. Is this right? Oh, no. Here, I'm adjusting the camera here. For that. Okay, good. I think that's what we need. Great. Sorry about
You
that.
can keep that over there.
Okay, that way we can see it, right?
Yeah.
Okay. All right, then here we go. Yep.
All right. No worries. In the case of the tower in London, it was a residential building, and they had this cladding material that was made of aluminum and polyethylene, which is a very combustible material. And that one was very flammable material, was not supposed to be there. So there was a fire in one of the apartments, and it easily propagated throughout the entire building through the outside. So the fire came from the outside to the inside. And a lot of people died there. It was very sad. Another one that here in the US, it was more remarkable was the World Trade Center, right? So we had the attacks. So the airplanes crashed against the towers. Do you guys remember where those airplanes were living and where they were going to? That was actually one of, oh, sorry, go ahead, Larry. Can you repeat that, please? No, okay. So they were actually living from Boston, and both of them were actually living from the West Coast and going into the East Coast. And the way they selected those flights instead of the other way was because the airplanes had a lot of fuel inside, right? So they have a lot of combustible material. So when they crashed inside of the towers, if you guys read about it, you're going to see that the towers remained standing for a couple hours after the crash, right? So it wasn't just the impact that caused the collapse between towers, but after that, you have this huge amount of combustible material inside of the buildings burning for a couple hours, and that caused a huge impact that also contributed for their collapse. So, for example, after 9/11, there was a lot of investigation in terms of how can we prevent progressive collapse in steel buildings as a result of fires. All right, so do you guys think we have this problem solved? Is fire still a problem in our society? Yes. Okay, do you hear a lot about home fires or fires in your neighborhoods, right? You probably sometimes hear the firefighters running their trucks around town. And I brought here some statistics for us to kind of visualize how this is still an issue now in our society. This is data from the latest report from the National Fire Protection Association, and Okay. All right. So in 2023, there were more than 1.3 million fires just in the US, just here. Okay. And a lot of injuries, a lot of people died, and a lot of property damage, of course. So just to give you guys a kind of a good understanding of what that means, because of a home fire, one person died every 3 hours in America during that year. Okay, and this was not like one specific year where we had a lot of fires. This data is very consistent for every year. Okay, so this is the latest report we have from 2023. But if you guys look back on 2022, 21, you're gonna get similar statistics. So it's a pretty concerning, right?
Like we still have like a lot of those instances. It's affecting a lot of our society. And we have to think about it, you know, as engineers, we're going to be building our infrastructure and buildings where people are going to live, work, study, get treated in hospitals. So it's really important for us to understand how, what is the behavior, the actual behavior of a fire. And when you think about fires, you probably think about temperatures, right? So temperatures are going to be very high, and that temperatures are going to be changing throughout the length of the fire event. We have here what we call a fire curve. So this is showing what is the change in temperature over time during a fire incident. First, we have, let's say we're all here in this classroom having a good time learning about fire safety. And I don't know, maybe somebody lights up a cigarette on the back of the room, or there's a candle and it gets on the floor. And then we have a carpet, right? This carpet's going to start burning. And that burning is going to start propagating throughout the surface of our floor. We have wood tables. You guys have your backpacks filled with books, papers. All of these are combustible materials. And fire, as the temperature keeps rising, the flames and the smoke and everything is propagating from one material to another, right? We even have plastic chairs over here. So a lot of combustible materials inside of this room. And once we, so these temperatures are going to be increasing slowly here right after the first ignition, up to a point where we call the flashover. So flashover is when, so when these materials are burning, they are releasing gases, and these gases are very hot. And they start accumulating on the ceiling because, you know, hot gases, they go up, they tend to go up. So they accumulate on the ceiling, and then the temperatures on the ceiling is going to be very high. And it's going to be radiating this high temperature into all the materials in the room. And once this layer of hot gases on the ceiling becomes too high, that's when we have what we call flashover. And everything that is combustible inside of the room starts burning at the same time. And we have this huge growth of temperature overall inside of this room. And then everything's going to burn. Once we burn everything that is combustible, everything that is plastic, wood, carpet, everything that can burn inside this room, we're going to reach our highest temperature, and then things are going to start cooling down, okay? And how can we design our buildings to prevent this from happening? So what kind of measures do you guys see in your buildings to prevent us from getting to this point? Yes. Sprinklers, very good. What else? Doors, fire doors. Fireproof coatings. Okay, that's a good one. Smoke detectors, right? So as fire extinguishers, a lot of things, they're there to prevent us from getting up to this point. Okay, so once we reach the flashover, temperatures are going to be so high inside here that we will not have any, like these electronic devices or anything like that will not be working. And we need to just make sure our structure is not going to collapse. Okay, so we split our fire safety measures into two categories. The first one is our active protection systems. So those that are going to start working when the fire starts. Okay, so sprinklers, they just start work. They're there, but they just start working once we have very high temperatures in the room, right? Fire extinguishers, they're there, but unless somebody picks them up and goes there, try to put out the fire, they're not going to work. After we reach this point, flash over, that temperatures are so high, people cannot survive that, then we will have another layer of protection that we call passive fire protection, okay? And this passive protection can be either, for example, building fire walls or fire doors to prevent the fire from propagating from this room into the next classroom or to the staircase, okay? And our structure, right? So if the temperatures are too high, we have two columns in this room. You guys, actually three, one on the back. So if the temperatures are too high here, you guys can imagine that these columns are going to lose strength, right? And at some point, they might not be able to carry the loads from the ceiling and everything that is above us. And that's when my research comes into place. Okay, so all that was to come to this point. So my goal is to design the structure of the building so that when we have failures on the sprinklers or smoke detectors or anything that can put out the fire in these early stages fails. Okay, so there's no people anymore inside. Firefighters cannot go in here. So we just got to make sure our structure is going to be there so it doesn't collapse, because as you guys can imagine, if these columns collapse, the ceiling is going to collapse here. I'm going to have a very high load on this floor, right? And then the entire building might collapse. All right, so we call, when we're designing the structure of buildings to resist fires, we have one specific property that is called fire resistance. Do you guys, how do you think we measure the fire resistance of a column or a beam or a slab? What kind of units do you use to measure the fire resistance? Is it a stress value, a temperature value? What do you guys think? Any guesses? Yes, Ethan. Time related, very good. So fire resistance is actually a unit of time. So when I'm talking about the fire resistance of this column, I'm going to say that it's 1 hour, 2 hours, 30 minutes. Okay, it's not a specific unit of load or temperature or deflection or whatever. Okay, because when we are designing the buildings and we are specifying the fire resistance of the structure, we again got to make sure there's enough time for people to evacuate, for firefighters to come in and put out the fire. So for a very tall building, we're going to need much more time for people to come from the top floor all the way down, right? But if we have a 1-floor building that has a lot of entrances and we have a lot of space for firefighters to go inside, we might need a lower fire resistance time. Okay. It also depends on the risk category. If we have a kitchen, right, we're going to have fire there, right? Because people are going to be cooking. So that also contributes for when the design code specify the amount of fire resistance we need for those buildings. Okay. So, all right, when we are evaluating our structures, of course, we got to make sure that we have enough load capacity, right? So we're going to have the load, the weight of the structure, the furniture, people, everything there. And as we're, hitting the structure, we're decreasing the strength up to a point that the strength is going to be below the loads that I'm applying there. So one of the requirements here is going to be that this capacity must be higher than the loads we're going to have during the fire, okay? Even after we reach certain levels of temperature. Deflections, if we have beams or slabs that deflect too much, they can never go back, okay? So we should also think about how their structure is going to behave after fires. And temperatures is also something important, especially for structural walls and floors. Let's say there's another classroom above us, and the temperatures, there's a fire in this classroom, and temperatures are increasing. So we have some level of insulation from the structure itself, but if the temperature on the floor above us, on the slab, gets too high, the fire propagates to the floor above us, right? So we want to minimize that. So temperature is also something that we take into consideration. So for these 3 aspects, we are going to assign a time that a structure, let's say we're analyzing this column, can maintain these three aspects in good condition. Okay. And we have different types of structures, right? Steel, concrete, timber, and they're going to have a very different behavior under high temperatures. And now we're going to talk about each one of them individually. Okay. All right, so let's first start with steel. Okay, we are in a steel frame building. You guys can see the columns here. And this picture right here is very, very interesting. It's very old. It might be a little hard to see, but it became very famous because we can see here 2 steel beams. This was after a fire, right? So you guys can see the steel beams here. And they're hanging over a timber beam. Okay. So why do you, what do you guys can see here? What is your thought when you look at this picture? Which one is stronger, steel or timber? Usually steel, right? But under fire, what happened to the steel here? It got soft, right? So as we start heating our structures, material properties are going to change. Our elastic modulus, for those of you who are from my macro materials class, goes down, right? And you guys saw that. We talked a little bit about this earlier this semester. So the elastic modulus goes down, and then we have a lot of deformation. So we have a lot of plasticity here. And the timber beam kind of was able to survive the fire, right? It's even supporting the steel beams over there. So from those three structural materials, steel, while it's the strongest material overall at ambient conditions, it is the weakest under fire. A conventional steel beam or column, if you guys get that beam and you put in a furnace and you do a fire test exposed to the temperatures of a real fire incident, the fire resistance of the steel beam is going to be around 30 minutes. Okay, so 20 to 30 minutes, sometimes even lower. It depends on a lot of factors. The load that we're applying. So if you had already a lot of load compared to the regional capacity of the beam, we're going to have a lot of stresses, and that will decrease the loads, the fire resistance. But overall, the fire resistance of steel members is much lower than concrete or timber. So how can we overcome that? There are a lot of ways we can protect our steel structures to prevent them from failing or collapsing during fire. The most common one, and it is the most common because it's the cheapest, right? It's going to be applying cementitious spray materials. So sometimes maybe you're in a coffee shop and you look up and you might see like this very rough thing around our steel structures. So we add this layer of mortar or shotcrete to protect the steel from the high temperatures. Okay, so this mortar here is going to work as an insulating material. Another way we can protect our steel members, gypsum boards. Okay, so this structure right here, at a first look, it kind of looks like concrete, right? RC. I took this picture at a coffee shop, and then I went there. I knocked. It was kind of empty, so it was gypsum. So they built this around the steel structure to prevent it. If there's a fire in this place, it gets protected. Okay. We can also use mineral wood. I also put here intumescent coatings. So don't worry, these columns that you guys are seeing here in this classroom, they are painted with a special paint. So if there's a fire here, this paint is going to start expanding. And if you guys come here after the fire, the structure is going to look like this, because this intumescent painting, once it get exposed to very high temperatures, it starts increasing in size and creates an insulating material. They're very expensive, so we're just using very special cases. Or we can combine steel with concrete and put our steel member inside of the concrete, and then the concrete works as an insulating material. All right, any questions so far? Yeah.
Have they used the insulation foam similar to the?
Oh yeah, they can. So there's a bunch of a lot of different insulating materials we can use. So foam is one of them if it is fire resistant, right? So and we are going to talk about design codes later, but we have design codes that specify, depending on how many hours of fire resistance we need, we're going to have different thickness here of insulating material we need to provide. Very good question. Anything else? Any other questions so far? No? Okay. All right. I'm going to share here. This was a project that I worked a couple years ago. I don't know if you guys heard about this, but this was a fire that happened on a bridge in Philadelphia on I-95. So there was a tanker carrying gasoline. It was going into Philadelphia to deliver the gas to a gas station. So it was coming down this road, And then the truck took the exit here. So it was gonna go underneath the overpass of the highway. And the driver lost control for some reason. And then it crashed against this wall underneath the bridge. And then there was a huge fire, as you guys can imagine. I think it was 8,000 gallons of gasoline. So it was a lot of combustible materials, flames. And I think it was 10 or 12 minutes after the crash, the bridge collapsed. Okay. So that was what we call a composite steel concrete bridge. So we had steel girders supporting a concrete deck on the top. And so as part of my research, we got the design plans, the regional design plans of the bridge, and we started doing some computational modeling. Okay, so we tried to model what happened, and we first modeled the fire behavior. So first we need to determine what were the temperatures that this structure was exposed. Okay, so what we did was we created the geometry of the bridge, and then we put where the truck was, the amount of fuel material we had there, and then we start running the simulations to kind of see what are the temperatures on each point throughout the length of the bridge at different points within the girders. And then once we had those temperatures, we ran a structural analysis. And for, again, when we were talking about fire, we were talking about time, right? So for each time, what was the temperature? And as a result of that temperature, what is the strength of the material? And that we could see, for example, if we add insulating materials, how does that increase or reduce the strength of the structure? All right, Danny, go ahead.
Big question. What software did you use to model the fire?
Sure. So for modeling fire behavior, we do what we call computational fluid dynamics. For this one, I used a software that was developed by NIST called FDS, Fire Dynamics Simulator. And therefore, I got the temperatures from here. And then for this one, I use Abacus, which is a finite element modeling software. Any other questions? No. Okay, so concrete structures next. So concrete is actually very good under fire because the main thing is it is much more insulating than steel. So what you guys are seeing on this plot here, the first plot, is the thermal conductivity of steel and concrete. So the line right here below is the thermal conductivity of concrete, and this red line here is the thermal conductivity of steel. So it's much higher than concrete, right? You guys probably have already got some piece of metal and expose one end to heating, right? So it conducts really easy. So when we have this, for example, these I-shaped sections for our steel structures, once we heat one side of the structure, the whole thing gets hot very, very fast, right? Whereas in concrete, once we are heating one of the surfaces, it takes a long time for the temperature, those very high temperatures to get inside. And in concrete, for those of you who are in structures, you might remember that. So in concrete, it's very good in compression, but very weak in tension, right? So to design, when we design concrete structures, we have to add steel rebars on the bottom to resist the tensile stresses we have on the bottom here of our beams. And during a fire, we have to protect these steel rebars because they're going to lose their strength very easily. Remember, we just talked about the fire resistance of steel structures. So when we're designing concrete structures for fire, we want to provide a layer here, a thickness of protection to the steel rebars. And that's how the design codes specify the fire design of concrete structures. Okay, so if you guys need 2 hours of fire resistance, they'll say you got to have at least 2 inches of thickness here. If you need 4 hours of fire resistance, you need 5 inches of concrete layer. Okay. But concrete is not perfect. And there's one little detail here that changes everything. And this is called spalling. Okay, so concrete has a lot of pores, right? And these pores, they're filled with moisture from water because we need water to make concrete, right? And when we start heating or exposing our structures to heat, what happens to water? When we heat water, what happens? Evaporates, right? So when water evaporates, that's an expensive process. So you're creating pressure inside the pores of the concrete. And that will cause the concrete to crack and sometimes even to explode. So there are a lot of videos online. If you guys look up fire-induced spalling, you're going to see structures like popping, pieces of the structure popping out and delaminating. So you're going to have these huge cracks that will decrease the capacity of the structure because you might have your reinforcement exposed, for example. How can we prevent that from happening? There are different ways. One of the most common ways is adding fibers. Have you guys heard about adding fibers into concrete? No? So, yeah. Any questions from Zoom? No. Okay. Okay. So we can add fibers to concrete. It can be metal fibers, steel fibers, or plastic, and that will change some of the properties. So once, if we have this very high tensile stresses caused by, this water evaporation, steel fibers will increase the tensile strength of our concrete. So it will help us prevent that. Another very interesting way is to use polypropylene fibers. So polypropylene fibers, they melt under elevated temperatures and they create these voids so the water can migrate and expand inside of those spaces that was previously occupied by the polypropylene fibers. So when we add these fibers, so these are some of the tests that I've done in the lab. So I got some concrete specimens, I put a pressure sensor inside and I put them in the oven, and then we heat them up and we measure the increase of pore pressure we have there. And once we add this polypropylene fibers, we can see a much lower pressure levels inside the material. So we can prevent those crackings and explosive spallings. All right, so I told you guys that concrete is very good under fire, right? And most of the time, our buildings are not going to collapse. But we got to make sure that the structure is still safe, right? Because the structure is still exposed to high temperatures. Okay, so we got to make sure that we still have enough strength so we can reoccupy that building. And so we have to perform what we call a post-fire assessment. And this is a fairly new topic. We are still doing a lot of research on this end because each fire is unique, right? So we have different materials, different geometries, a lot of things that change from one building to another. And we have a lot of methods and techniques that we can use to evaluate the condition of concrete or other structures. So in this case right here, so what we did is, all right, so this building was exposed to fire. We had very high temperatures on the surface, but we don't know how deep those temperatures got inside of the member, right? So what we did is we started collecting samples at each depth through all the cross section of our structural member, and we analyzed the microstructure of the material. And we are able to identify changes of phases that was in the microstructure that was telling us which level of temperature was reached there. And with that information, we could backward calculate what is the residual capacity of those beams and columns in that building and determine if we had a very significant loss of strength. right? So I hope you guys are kind of getting the idea that I'm trying to put right now, that structural fire safety, even though we are analyzing the structure, goes beyond just the structural design, right? So we have a lot of things related to the architecture of the building. So what do you guys think will influence on the temperatures we have in a room during a fire? Width of the room, right? So the size. Mm-hmm. The amount of combustible materials, very good. What else? Mm-hmm. The type of materials. Airflow, very good. So if you have openings, right, doors, windows, that will affect the ventilation and therefore the temperatures. So all that will affect our design and sorry, our fire conditions. So every scenario is unique. And so we are not only on structural analysis anymore. We have the architecture, the conditions of the building, which is pretty much just fire science, right? We also have material science because we have to understand how the material behaves under elevated temperatures. Going back to the microstructural level, because those very high temperatures are going to change basically the material that we have there. Okay, and that all that combined will have an effect on the structural behavior. Okay, the last topic that I have here is going to be timber structures. And to be honest, this is a fairly new topic for me myself. I just started studying and working with timber structures. I have two students here that are working with me, Ethan and Miguel. We started working this semester. And what do we have here? Is a picture of the Ascent building in Milwaukee. Have you guys heard about this building? Ascent building, right? What is it known for? Do you guys know? Mm-hmm.
No.
It is the tallest timber structure in the world. So mass timber is pretty much just a combination, or we are going to glue together lumbers of different lumbers together to make larger structural members. Instead of getting like a whole, instead of making a beam or a column of a single tree, we're going to get different slices of lumber from different trees, and we're going to glue them together to make our columns and beams. And doing that is not something new, but we don't have design codes for that yet, right? So we're still learning and developing that. So that's why this building right here is so unique. It was open, I think, 3 years ago. And every year we have new designs, new solutions coming to the world of mass timber. But one of the main concerns when you talk about building something tall with wood is fire, right? Because again, you have this very tall building, and if there's a fire here, people need to evacuate. And when you talk about fire and wood, people get scared, right? So these pictures you guys are seeing here, these are the columns of this building. So before building this, they had the columns tested in a laboratory. So they have a big furnace. They put those columns inside of the furnace. And then once you burn them, you're going to have a reduction of the cross section. Okay. And but one thing interesting about timber compared to steel and wood, okay, wood burns. Concrete and steel, they don't burn. Okay, they lose strength, they change properties and everything, but they don't burn. Wood burns. But the interesting thing about wood is that once it burns, it creates what we call a charred layer. Okay, so you have that burnt wood on the outside, and I have a picture of you guys. I didn't ask for it, but basically, we have here a char layer on the outside, and that layer remains there for most of the time. Okay, that charring remains in the outside of our structure during fire exposure. So when the flames or the hot exposure is hitting on the side of our structure, it prevents the high temperatures from reaching the inside. So we have pretty much like a sacrificial layer all around of our structural members, and we can keep the inside protected, so we have most of the strength still available. Okay, so that's how timber structures can resist fires. And of course, there are a number of factors that affect that. So we're now using glue to put wood together, right? We have moisture inside of the wood that we need to account for. And that's what we're trying to investigate right now. So how different levels of temperature are going to affect the strength of the material. So I have here a picture of Miguel and Ethan last week in the lab. They were tensioning this wood specimen. And this was not exposed to high temperatures. We are going to do that next. We are still developing the setup here for testing that. They have burned some wood. And they're also analyzing the microstructure of that, so we can understand what is the interface here between this charred layer and the part of the wood that is still intact. So there's still a lot that we are learning from wood under fire. We know it can behave well, it can be good, but it's that affirmation is very sensitive right now because wood is a natural material. We don't have a lot of control over how we grow wood, right? Like steel that we're doing in the factory, or concrete that we have more knowledge about the materials you're putting inside. With timber structures, we are still have all those unknowns that we need to account for. All right, so and how we design structures for fire nowadays is pretty much what we call a prescriptive design. And that's how most codes are written. So this is the table that I got from AISC 360, which is our steel Bible. So every time you see a student walking with a gold yellow book, that's our steel Bible. On one of the appendix on the back of that manual, you guys will find this table, and it specifies the minimum fire protection and fire resistance rating for steel assemblies. So you have here, for example, steel columns and all primary trusses, okay? And then you have here different categories, and you guys have what we call the minimum thickness of insulating material for fire resistance times. So for example, if you need a fire for that specific building, the firefighters ask a fire resistance of 4 hours, you need to provide 2.5 inches the thickness of the insulating material around that. So if you need 1 hour, just 1 hour, it's going to be 1 inch. Okay. So the higher the fire resistance time you need, the higher is going to be the insulating material. For concrete, for those of you who are wondering about concrete, we have ACI 216, which is the design code just for fire resistance of RC structures. This code, they have a similar table like this, but instead of specifying additional fire insulating materials, we're just going to specify a minimum thickness of concrete thickness for our rebars. And the last one here is our fire design specification for wood structures. They just got a new version last year, and what this one does is, okay, so we are going to have charring, right? So that thick charred layer around our wood beams or wood columns, this is increasing over time. So we are losing a little bit of the cross section every minute throughout fire exposure. So depending, they specify, for example, 0.58 inches per minute. Okay, so you're going to lose 0.5 inch every minute of fire half millimeter, of every minute of fire exposure. So depending on how much fire resistance you need, you guys will find out what is going to be the remaining cross section you guys have there, and how much strength your structural members is going to have. All right, so this is pretty much just prescriptive design, okay? So these tables, these codes, they're giving us the specifications. We're just following it, okay? That they're not concerned about the specifics of our buildings or structures that we are designing. So that's why there's a lot of interest in the industry for what we call performance-based design. And this has been on cover of magazines for structures, of course, right? And there's a lot of talk about how we can shift, or not for all cases, but for specific cases, from those regulations that are very strict into something that we can analyze our specific building and maybe provide a design that is more efficient, okay? Because maybe, I don't know, I'm designing this school building and I have very large windows. If there's a fire, those windows are going to break. Wind will take most of the heat out. Do we need that much fire protection? So if you're designing using these codes, we don't have other option other than just follow these tables, okay? But if we're doing performance-based design, we can analyze, run those type of simulations that I showed you guys before, and get the actual temperatures you're going to get in that room, and get the specific material properties of our. Let's say we are working for high strength concrete. Let's say we are adding fibers to our concrete that will increase the fire resistance, right? So that's what we call performance-based design. A very good analogy of that is when you guys are cooking. Sometimes you're just following recipes, right? So I'm Brazilian. I love steak. I love to do my steak, and sometimes people, like when I was beginning, sometimes I was just following recipes, right? We need 2 minutes on one side and 2 minutes on another one, and then you're gonna rest and put it in the oven. Or you're gonna use a thermometer to get the specific temperature. But maybe I like my steak more rare or more medium, right? So as I learn how to cook steak, I can make the steak the way I want. I don't need to follow one specific recipe. So it's just like that when you're doing structural design. Okay, so one way would be following the recipe as it is. The other way is, okay, I'm going to do these measurements. I'm going to use the exact temperature inside of the steak to determine when it's good enough for me for this case. Okay, so a few more pictures just illustrating what would that be. For example, for running those fire simulations. Okay, so depending on, for example, the length of the bridge, the height of the bridge, the amount of fuel I have. This is, for example, a 75 megawatts. This is a 200 megawatt fire. I'm going to have different temperatures and different fire conditions, and that will affect the structural behavior, even how my structure is gonna fail. Okay, so that's what performance-based design is. I just wanted to mention it a little bit because I think it's something that all of you, maybe not right after you guys finish college, but you'll hear about this as you start attending conferences, technical conferences, and talking to other experts. Or sometimes you're gonna have one specific project and the client wants to save, let's say you have a huge building. Do you need to fireproof all the columns in that building, all the beams, right? So if you guys are following a prescriptive-based design, yes, you have to follow that. But if you guys maybe are able to run those analysis, you can say that maybe you don't need to fireproof all the columns and beams on that building. You can do a selection and then save a lot on your design. But it's still being safe, right? So safety is the primary thing. All right, and before I finish here and open for questions, I have this picture, and this is kind of how I got into this field. It was not a random decision on my end. Okay, I'm going to study fire safety from now on. So when I was in college, just like you guys, there was a big fire in a nightclub nearby my hometown. 243 people died, college students, people around my age at the time, in this incident. And I got really moved and I wanted to do something to help society. So At the time, this particular incident changed a lot of the fire regulations back in Brazil. And so that's how I started working with this. I have a professor in my university working with fire safety. So I teamed up with them, and it was 12 years ago. And since then, I've done a lot. I shared a little bit of the things I've done over the last few years. Yeah, so I'm gonna leave the floor open for questions now, and thank you for your time.
All right, questions. And then if you are on Zoom, you're welcome to type your question or just unmute and ask questions. Anyone? What part of Brazil did this happen in?
South.
Can you repeat the question so that they can hear?
What part of the of Brazil was the fire in?
This was in the south of Brazil. It was a city called Santa Maria. It was about an hour and a half away from our hometown. Yeah. I was checking with my wife. She's in the back there.
What kinds of you said like you worked with a professor at your university. What kinds of things did you do to get into fire safety specifically? Like,
Very good question. So at the time, we didn't have a lab or anything at all. So and most of the fire codes were international. So we didn't even have anything in Portuguese, for example. So at the time, we started seeing, okay, so what are the tasks we need to do to make like our designs more safe? Okay, and we split up into two parts. One, what we call fire resistance, that we talked a lot about here. Another thing, and that was the main cause for this incident, is what we call fire reaction. So, for example, we talked about carpet, right? So when the carpet burns, it releases smoke and gas, and this gas can be toxic. And that was the case on this fire. So in this case here, most people died because of the toxic gas that was released by the burning of the acoustic insulating material on the ceiling. So it was not even because of the high temperatures. It was mostly because of those insulating materials. And then after that, I always had a passion for structure, so I combined both for my research. Yeah.
What have people done to make materials more fireproof, like the carpeting and gypsum boards?
So gypsum is not combustible. Okay, so it's not gonna burn. We can classify actually all building materials as either combustible or non-combustible. So combustibles are things that are gonna burn. They catch fire. Okay, paper catches fire, right? So plastics catch fire. You can change the chemistry of the material so they don't become flammables, or they don't sustain flames, or you can improve that. It's just like it's going to increase the cost of the materials. So when we have things like this, or the building we talked about in London, that's when like some people make bad decisions, right? So they choose the cheaper option over the safe one. So we can make, I'm not saying like you should never use those types of materials, but you got to know what you're specifying, right? And in order to know that, you need to understand what is their behavior under elevated temperatures. So are they going to sustain flames? Are they combustible? Are they going to release gases? Or even sometimes it's not even about that, but if you have a smoke that is too dense, we cannot see, right? If the smoke here on the building gets too dense, we cannot see, we cannot go out, we're going to be lost. Am I right? So that's another factor. And that all goes into what we call fire reaction. And fire reaction is a property of the materials. Fire resistance is a property of the structure. Okay. And remember the fire curve? So fire reaction matters in the beginning of the fire. Fire resistance works after the fire has fully developed.
I have a question. You mentioned about the bridge. Right now, we still don't have fire cold as a bridge?
No, it's not required.
It's not required
No.
because we probably assume the bridge go over water, so the chance of being burned is very
Yeah.
rare.
So there, first of all, bridge fires, they don't represent a high risk for people because they're open spaces, right? So if the truck there caught fire, there's a very limited number of people that is going to be around that area, right? So the primary objective of any fire safety measure is to protect people. And that comes with a cost, right? And as you guys can imagine, the probability of having a fire on a bridge is very low because, you know, that's a single point on the highway. So you have a very long highway, and for the truck to catch on fire on that specific point, the probability is very
So the
low.
case study you mentioned about in New Jersey, that's just bad luck. I mean,
It was bad luck.
the truck just hit it and then it just burned
Yeah.
the whole bridge down.
Yeah, and it's interesting because I mean, it's always a balance, right? So is it more thinking about cost, because cost is the most sensitive organ of the human body, right? Our pockets. And if you think about it, you know, like, are you going to protect all the bridges? You know, it has a very high cost. Like, are we going to replace the 1 or 2 bridges that catch fire in a year? Like, how does that compare to one another, right?
Right.
Maybe instead of protecting all the bridges, can we protect just the critical bridges? So let's say we have a hospital and a bridge that is the only access for that hospital, right? So that's a very critical bridge, because if that goes down, like, people cannot go into the hospital, right? Or landmarks like the Golden Gate, right? You have all those steel cables there. Brooklyn Bridge. So those are another types of structures that. So we can analyze that's another field. I also be involved in research related to that. So, okay, we don't need to protect all the bridges. Maybe we have a bridge like in a very rural area that, like, maybe 10 cars a day crosses the bridge, or we have a bridge in a very busy urban area that we have like 100,000 cars crossing every day, right? So which one will get priority? And as I said, concrete resists the high temperatures much higher than steel. So what we saw there, that bridge is made of steel. But someone mentioned LA, was it you? Yeah, so the bridge in LA was made of concrete. And most of the bridge remained, it didn't collapse, it was there. We just had a lot of spalling and a lot of lost strength. We had to repair that. So it was closed for several months before it was reopened. That's chaotic, especially for LA, right? We already have a very busy traffic. But in terms of life loss, very low. In terms of, so as a society, we're always balancing risk and gain, right? So, and that's how code developers they create those codes and specifications.
Any other questions from the house? Okay, pass. Yeah, we'll do one last one and then we'll go to the Zoom.
So what is the reality of, say, maybe saving a structure after a fire? I know with a lot of the things we talk about is like keeping things so that we can people in the building can escape and that firefighters can go in and stop the fire. As part of that, also to maybe try to lower the costs of like rebuilding the building, or is there ever a hope of rebuilding?
Yes, and that's a new concept that we call fire resiliency. So resistance is when we just want to resist the fire, okay? So we're not worried about after the fire. So we have those minimum requirements, deflection, temperatures, whatever, to make sure the building is not going to fail during the fire. Resilience is another concept. So when we're talking about fire resiliency, we're talking about, okay, so we have the fire, we reach that temperature, the temperature goes down. So is the structure going to be able to have the same characteristics or minimum, like what is the minimum properties we're going to need after the fire? So that's a very good question. And again, it comes with a cost, right? For critical buildings, embassies, consulates, things like that, the White House, you know, like those very critical buildings, hospitals sometimes, they are designed for that, okay? But for, I mean, it really depends on the budget. If the owner is willing to, right? We can do it.
All right, then we'll do, there's one question from Zoom and then let's answer that question and then we can close the presentation here. So how do you analyze or model a burned wood beam or column that is composed of many various pieces and burn rate? Wouldn't it be very long uniform member after burning? So the wood, because the column is made of different pieces and then you glue them
Okay,
together.
we're talking about mass timber.
Yeah, I think so. I
Yeah.
assume so, yes.
So from the research we have right now, the glue, so that we have different types of glues that can be used, and there's new type glues coming out every day. But for those that are designed for fire resistance, they have shown that the material pretty much behaves uniformly. So in terms of burning rate and charring rate, it is almost the same thing as a just a timber, a whole timber structure without any glue inside. So that's what the research has reported yet. But like we here in Platteville, we're just starting, so we haven't actually tested ourselves that.
And because the columns are so big and then they have crossed so many different directions.
Oh yeah.
And then it actually solves the problem of wood, which is, you know, the properties are different at different directions.
Oh yeah, yeah.
Yeah,
Mhm.
but because you cross it, actually you make them uniform now,
Oh yeah. Mhm.
right?
Exactly.
So I think that's one reason
Yeah.
why they're using the cross
Mhm.
laminated timber. So, yeah. Does the burning rate of timber vary depend on the species?
Yes.
That'd be so, yeah.
Yeah. It's not a lot, but it does change a little bit.
Yeah. Okay, how about that? We'll do this. It's already 6:02. First, I will officially end the seminar, and then I believe the speaker will stay. If you have any questions, feel free to ask. And then there's still more pizza. Feel free to take them. Yeah. So, well, please help me again. Thank our speaker. Thank you very much. Thank you. And then for those who need PDH answers, please go to the Engineering Now Seminar website, and then you can request your PDH certificate from there. Okay. All right. Thank you again for joining the Engineering Seminar series of the semester. We'll see you in spring, which will be starting in February and March. So thank you very much. Where is the stop recording thing? Here it is. There we go.